So good morning students. So now we discuss double field revolving theory, which explains why a single phase induction motor is not self-starting. So what does it say? See, you have an alternating quantity phi which is given by phi m cos theta. So it says that every alternating quantity you can divide it into two other quantities, say phi 1 and phi 2, such that phi 1 equal to phi 2 and it is given by phi m by 2, where this phi is equal to the magnitude, the amplitude of the original alternating quantity. That is, if you are having a 4, you can split the 4 into 2 and 2. And if you are having a 6, you can split into 3 and 3, equal parts. Okay, similarly, every alternating quantity phi m cos theta can be divided into two components, phi 1 and phi 2, where these phi 1 and phi 2 are other two alternating quantities having same magnitude and they are rotating in opposite directions, such that this phi 1, if this is phi 1 and phi 2, they are of equal magnitudes and they are rotating in opposite direction. That is, if phi 1 is rotating in anti-clockwise direction, phi 2 will be in clockwise direction. That is double field revolving theory. And to prove the theory, I am starting with a result. That is, I am having phi 1 and phi 2 with me. That is, I am having a 2 and 2 with me and I am combining that 2 and forming a 4. Or I am having 3 and 3 with me and I am combining it and producing a 6. Similarly, I am having a phi 1 and phi 2 with me. Equal vectors. Two equal vectors rotating with the same speed, say ns. Okay, your synchronous speed. Okay, you are having phi 1 and phi 2, two equal vectors which are rotating with the same speed in opposite direction. Let phi 1 will be rotating in anti-clockwise direction and phi 2 in clockwise direction. So I am starting with the first point, that is when theta is equal to 0. At the 0th instant, what happens? So this is the condition. If you have phi 1 and phi 2, two equal vectors lying along the x-axis. So what will be the resultant? That is phi 1 and phi 2, phi 1 plus phi 2, where phi 1 is phi m by 2 and phi 2 is again phi m by 2. That gives you the resultant phi m. That is, at the instant 0, you are having the resultant phi m. Again, I am rotating these vectors 90 degree. That is, phi 1 is rotated in anti-clockwise direction, phi 2 is rotated in clockwise direction. So where this is phi 1 comes, phi 1 rotates at 90 degree and now the new position of phi 1 is this. Again, phi 2 is rotated in 90 degree and phi 2 attains the position here. So at the instant of theta equal to 90 degree, your two vectors phi 1 and phi 2, the new position is this. So what will be the resultant? Phi 1 plus phi 2, that is two equal vectors acting exactly opposite. The resultant will be 0 degree. 0. Okay, again the next instant, I am again rotating it by 90 degree. That is, phi 1 is rotated in anti-clockwise, again 90 degree. So the new position of phi 1 is this. And phi 2 is again rotated clockwise 90 degree. The new position of phi 2 is this. That is, a total of 90 plus 90 gives you 180 degree. So theta is 180. So what will be the magnitude of resultant? Phi 1 plus phi 2. Both phi 1 and phi 2 are acting in opposite directions. That is negative x-axis. So it gives you minus phi m by 2 plus minus phi m by 2. So the resultant is minus phi m. Okay. So again, if you are having another 90 degree rotation, that is theta is equal to 270 degree. Again, what happens? It will be like this. So phi 1 is rotated again. If it is 270, phi 1 will be downwards and your phi 2 will be like this. Okay. So the resultant will again be equal to 0. So I am just pointing out the instance, that is when theta is equal to 0, you have phi m, theta equal to 90, you have 0, and theta is equal to 180, you have minus phi m. So if you are plotting it, what does it give you? Y and x axis, theta in your x axis. So the resultant of phi 1 and phi 2, at the instant 0, it gives you phi m, at the instant 90, it gives you 0, at the instant of 180, it gives you minus phi m. Again 270, it gives you 0. What is this wave actually? It is a cosine wave. Okay, this is actually the original wave phi, which is given by phi m cos theta. At 0 you have the maximum, at 90 you have the 0, and at 180 you have the negative maximum, at 270 you have what? Again the 0 value. This both waves, the wave of phi, which is a cosine wave, is same as the wave of phi 1 plus phi 2. That is, from phi 1 and phi 2, if you are combining phi 1 and phi 2, the resultant will give you another alternating quantity phi. So just reversing it. If you are having two equal vectors and the resultant gives you an alternating quantity, so if I am telling it in reverse way, that is, every alternating quantity can be divided into two equal vectors which are rotating in opposite direction. That is actually double field revolving theory. Then now, the thing, my point is to tell you why the induction motor is not self-starting. So I draw the torque slip cara of an induction motor. So I am having a point torque slip cara. In x-axis I have the slip, and in y-axis I will be drawing the torque. So I'll start with slip is equal to 0, slip is equal to 1, and I'll reach at slip is equal to 2. So my starting point is slip is equal to 1. So starting point means the rotor speed nr should be equal to 0. So slip is equal to ns minus nr by ns. That is, x starting, rotor is stationary, nr is 0. So what will be the value of s? nr becomes 0, so ns by ns will give you 1. So this is the starting point, slip is equal to 1. So let's start from here. Again, you have two flexes, phi 1 and phi 2. My original flex have been divided into phi 1 and phi 2, two flexes, where phi 1 is rotating in anti-clockwise direction. I will call it as a forward flex, which gives you a forward torque. Again, I have another flex, phi 2, which is rotating in clockwise direction or backward rotation. So, which gives you a torque, backward torque Tf2. So, I have two torques, forward torque Tf1 and backward torque Tf2. So, I'll be having two torque caras for the speed or the slip. So, first I'll plot the forward torque slip cara, which is similar to a three-phase induction motor. So, I'll start from the point slip is equal to 1, which is the starting point. Okay, at starting I have a starting torque. This is the starting torque of for the forward torque. Okay, let's start from this point where the rotor speed was 0 and rotor acquires its speed, and the rotor speed reaches what? Rotor speed reaches the synchronous speed, and at synchronous speed the torque value will be equal to what? The torque value will be equal to 0. Again, what about this portion? S equal to 1 to S equal to 2. This is the braking portion for a three-phase or a single-phase induction motor. Okay, that is, the speed becomes negative in this region. So this corresponds to the forward torque Tf1. Again, what is the condition with the backward torque? So backward rotation is actually what the speed will be opposite to that of the forward field. So again, I have a starting torque which is exactly similar to this. Okay, then how the machine goes? The torque slip cara will be like this. Okay, for this backward field, this will be what? This will be the braking area. So the forward field, this is operating region, and for the backward field, this is the operating region, because the speed is just opposite, direction of rotation is just. So at every instant you have two torques, and the resultant torque will be the sum of Tf1 and Tf2. So Tf1 plus Tf2, where Tf2 has a backward or anti-clockwise rotating torque. So the resultant will be Tf1 plus Tf2, which is actually Tf1 minus Tf2. Okay, so let's start from this point. You have a 0 Tf1 and a negative Tf2. So this will be your starting point. It starts from here, and at every instant here you have a positive torque. Now, at this point what happens? Tf1 equal to Tf2. So your resultant torque will be 0. Again you have a torque like this and like this. Okay. So my point is a starting point where the Tf1 and Tf2 is exactly equal and opposite. So at the point of starting, the resultant torque of the machine will be equal to 0. That is, at starting, there is no torque produced in a single phase induction motor. Or torque is produced, two torques are produced which are equal and opposite, so the machine cannot start. So by some means, we have to introduce a torque at this point so that the machine will start running. Rest all other portions are having resultant torques except the starting point. So if you are making some adjustments so that some torque is produced at this point, the machine will start and it will run. Okay, so there are many methods for starting a single phase induction motor that we can discuss in another video. Thank you.